Okay, let's see if we can program up a solution to this problem on the spreadsheet. I'm going to start out, I want to get the delta t in there. I think the way I'm actually going to go is I'll create an integer value I'll call capital N. I'm going to start out with 1,000, representing how many data points I'm actually going to use, and then T sub f I'll put in here, and I'll calculate what delta t is from those two values. So the final value of t, I think it's 2.38 seconds. Let's see, yeah, 2.38 seconds is this one right here. So 2.38. And then my plan is my delta t, I just got that dt, is going to be equal to 1,000th of this. So that slash just whatever n is. Okay, what else do I need in there? Gotta put, I need c, which is what I'm going to be changing, and m. So I'm going to start with 0 for c, and that is what I'm going to be changing. I think I'll make that red and bold, so we'll be playing around with that one. And then m, that's 0.008488 kilograms, I think. But yeah, and then I need a sub c, 0.6666 meters per second squared. That's a sub c. And then we might just need a couple more things, so I think I'll leave room. And get my table started. So I need n, t sub n, x sub n, v sub n, a sub n, v sub n plus 1/2, and a sub n plus 1/2. Alright. Now the n's, I'm going to start that with 0. This will just be equals the one above it. I'll click on the one above it. Plus 1. So that makes that a 1. Copy that down one more. That makes that a 2. Yeah, that seems to be working. This, the t sub n's, it's equal to the n. I'll just click on it to get it in there. Times the delta t. I'll click on it, but I want to make it absolute, so it always takes that 1 in the third row, so I'll put the dollar in there. So it's $3. And then, so the first one should turn out to be 0.238, and the second one 0.4 something, so that's looking good. And then here, x0 starts out as a 0, and I think I'll work this whole row across. Vn starts out as 0. An is equal to AC, so I'll hit equals. AC is this guy, again with absolute addressing, put the dollar sign in there. And then minus, so minus sign, C over M, I've got the C in there, C with a dollar, slash M with a dollar, and then times, so star, V sub N, which is just whatever's to the left of it. Click on it and hit return. Alright, So it starts out at the 0.666, that constant term. And actually on mine, so far since I got that set to 0, they should all be that. Okay, Vn plus a half. Okay, that's that real approximation there. I mean, they're all approximations since we're using finite time intervals, but this is, let's call it the worst approximation. The quantity to the left of it times delta t with a $sign /2. Okay, and then this thing actually just looks just like this formula. I'll copy it and paste it, Control V, and then take a look at it. So it's supposed to be $6. It's actually supposed to be A sub C, which is $6, and then minus $4 should be minus C, that's $4, slash M, which is $5. So far so good. And then times F10, which is the quantity just to the left of it. C5. Yeah, I'm not really seeing why that's a 0. Divide by 0 error at this point. So let's, the divide by 0 would be $5. Oh, these are all supposed to be A's, so it moved it over 2. I wanted A's in there. $5. Okay, and then it should actually be the same as that one, so that's cool. Alright, then x sub n is whatever the one before it is. So I hit equal sign, click on the one before it, and then plus v, the half one before it. So that would be that. So I hit plus, and then this one times, I'll hit the star key, the asterisk, and then times delta t. That's this guy right here, except I need the $sign. Alright. So that looks good for x sub n. And then v sub n is the one before it, so I hit equal sign, click on the one before it, plus the a from the one line before it in the plus a half place. So that'd be this thing, and then times the delta t with absolute addressing. Alright. Then a sub n is the same thing as what it was. V sub n plus a half is the one before it, so I'll hit equal sign, click on the one before it, and then plus a sub n, the current a, that's that one, and then times the dt, so with a $sign. It doesn't actually look like it came out quite right, so I got the second term, but I need this guy right here, the v sub n minus half, the one before it, and then plus that. Alright, so I think it took that time. And then this guy is just that. Alright, I guess I want to, this is the one before, check a little bit, the one before it, plus the G10, it looks good, plus this guy, and then times the delta t, and then this one is the one before it, it's the F10 plus E11, the current acceleration, that looks good, times the $3. Alright, and then for the next line, it's just everything copied down one. And in fact, from then on we should be able to copy that down for 1,000 values. So let's do that. It'll take me to about 1010, maybe 1009. Yeah, I made that be 1000. The acceleration didn't change, and that's all because I got that C set in there. Alright, let's take a look, see what this looks like. We'll do a graph of x versus t, so t comma x and be this set of values. And I'll do a scatter plot, connect the dots. I go next, I'll just call it x versus t, where I'm plotting t on the x-axis and x along the y-axis. Call that a finish, get rid of that. Trying to make it a little smaller. I'd like to get it up to the top here. See how small I can make it and still be able to see what's going on. See if I can get 3 of them in here. Alright, that's just... I'll try that. Control C, I'm just going to copy this graph down here. Control V. I slid it down instead of copying it. Alright. So this one I want to call V versus T. And I'm going to do a right click, source data, series for the second, for the Y values I want to go over to the next column, so that would be D. And that's what V versus T looks like. So constant increase, that's good because I got constant acceleration so far since I haven't changed C yet. And then copy that one. I go Control C, click right there, do a Control V. You can slide it up a little bit and change that to A versus T. Change that to an A. I'm going to right click, source data, and go to the next column over. That's column E. See if that works. In column E, I do have the acceleration, and it's showing the constant acceleration at about 0.7, and yep, that looks good. Alright, so let's play around with C and see what happens. I'm going to try, let's say, 0.01. And it looks like this is making sense. As the thing speeds up, the acceleration should get smaller and smaller. And the velocity gets bigger and bigger, but then it's approaching some constant value, which I would call the terminal velocity. At the terminal velocity, the upward viscous force, the downward viscous force is equal to the amount by which the buoyant force exceeds the weight force. So it's speeding up on the way up, but ever slower until the velocity gets so high that the retarding force makes it so that it can't speed up anymore, and then from there on it just goes at a constant speed. Alright, I want to indicate in here, I'll call this XF, X sub F, and that was given, the final value of position, you know, the position for the top of the bucket. It's some given value in the problem. They said, I actually calculated it. They gave us the depth of the bucket. So XF is 0.3011 meters. 0.0311 meters. And I want to see how far it actually went. So this, I'll call this X sub n. So it's the X value, it's the very last X value. So, because I want them to match is the thing. So my last x value, I'm just going to say this is equal to, and then I'll go all the way down to the bottom, and it's the third column. The x's are right here. So x sub capital N would be this value right here. Hit return, and scroll back up there. So, alright, with this C value, looks like it's going way too far. It's going almost a meter. And we want 3 centimeters. That doesn't actually make sense to me. So I did this, 0.3011, not 0.03. I did this in a bucket, and it was, about 30 centimeters deep. So 0.3011. 0.3011. Okay, so we're at like almost a meter. I want a third of that. Let's increase C and see what happens. I'll go 0.02, and still it's going too far. I'll put that one in blue. The thing I'm tracking here is how far it goes, but with this C, pretending the water is whatever depth, and it's going too far. We want it to only go about half that. I'll try 0.05. Okay, things have gone haywire here. It looks like the velocity, the acceleration got down to 0, but then it came up again. Let's see if I can make it. And this thing's still going too far. It's not working quite right. So we'll type in a 0.04, and we can see everything's working out fine. Velocity goes up to some constant value. The acceleration comes down to 0, but then it's going positive after that. Let's check to see if we got the right terminal velocity. So I want to go back here and solve for the terminal velocity. At the terminal velocity, the acceleration will be 0. So we got this expression for the acceleration. What happens as the velocity gets bigger and bigger, this gets closer and closer to 0. And then the velocity gets up to a certain amount, the acceleration is 0, and the velocity stops changing. So once the acceleration is 0, and in our numerical calculations, something's going wrong that's making it so that it goes down to 0 and then it starts coming back up again. And I think it's, if we look at it down here, so I got the acceleration at 1.5. It goes negative. It's essentially 0, but call it round off error. It just barely goes negative. And then I think that's where things start going haywire. So let's see. It's saying that our terminal velocity should be about 0.14 something. Let's see how that actually, see if that agrees with what we can figure the terminal velocity out to be. So at the terminal velocity, A equals 0. So in other words, using this equation right here, we have 0 equals AC minus C over M times VT. So VT is equal to M over C times A sub C. VT is equal to M over C times A sub C. So I think I want to take a look at what VT, the value of VT is. So I'm actually going to stick that in here. We'll call that V sub capital T, the terminal velocity, and I'm claiming it's equal to, and M, that's this value, slash C, that's this value, times, all that times A sub C, that's this value. And so it should come out to be like 0.1414. And I'm actually going to go, let's look at v sub n. Like the last value. If it got up to the terminal velocity, v sub n should be equal to the terminal velocity. And this will be, I'll hit the equal sign and then just scroll down to the last one in this column, D. So it's that one. And hit return and slide back up. So our terminal velocity is not equal to that value. And indeed, what happened over here, this one got negative. That changed the acceleration, and so things definitely got mixed up. I think what I'll do is look down here to where the acceleration started going negative. And what happened is our velocity got up above the terminal velocity. So I think, and it happens first in here. This one's a little bit bigger, of course, 1.4, yeah, compared to that one. So it first happens, things first go wrong in this guy right here. So I think I'll work with that one. And if I recall that this is just a copy of what's above it. 2 is a copy of 1. Yeah, 2 is an exact copy of 1. So I'll change something first in row 1. This guy right here can go bad. We'll say up here what I'm going to do is say, I'm going to say it's equal to that, but only if. So if this quantity that we just calculated is less than the terminal velocity, which is this value right here, and I'm going to use $2 there and make sure it's always getting that one exact value. But if it's less than that, if it's less than the terminal velocity, then we'll leave it as it was. So then I'll just copy this piece that we calculated. So Control C and Control V. So it's just what it was if it's less than the terminal velocity. Otherwise, we'll say it's equal to the terminal velocity. So we don't let the acceleration make it go beyond the terminal velocity. So we know it can't. Once the acceleration goes to 0, it should just stay at the terminal velocity. So we're going to force it to be the case, not let any round-off error mess us up with that tiny negative number, gets things started in the wrong direction. Alright, and then okay, I want to fix up this this next line as well. So if this thing is at the terminal velocity, then the velocity should always be at the terminal velocity. So I'll do another if here. If open parentheses, this quantity up here that we just worked with is less than the terminal velocity, $, get back where I was, hit a comma, then we put in what we calculated, that's already there. Otherwise, we put in the terminal velocity. And always that actual value, so I'll put the dollars in there for absolute addressing. Okay, I think that's perfect. The acceleration, if we're at the terminal velocity, should just be 0. So I think I'll look at this one, which is calculated based on that one. So for this acceleration right next to it, if the velocity next to it, which is what we're using, is less than, there's the less than symbol, the terminal velocity, so I'll click on that, but I'll put dollars in front of it. Then use what I calculated. Otherwise, I should be using 0. If we're at the terminal velocity, the acceleration should just be 0. Alright, so I've changed these two. I've changed this one. I also want to change this one. Same kind of thing. The same thing that I just did. If this quantity is less than the terminal velocity, is less than, I'm going to do an escape out of that one, and I'm trying to change this guy. And I think I'm going to do control. Did I make any changes to that one? No, it looks pretty much the same as the one before it. Actually, that's where it came from, so copy it down to there. That's what I had. And then try changing it again. So I wanted to put in an if, open parentheses, so this quantity is less than the terminal velocity, dollar. Hit the right arrow key to go there before. That's what I should just be clicking with the mouse so that it doesn't accept the answer. Comma. Okay, if it's less than the terminal velocity, use the calculation that I created. Otherwise, the acceleration should be 0. So if we're at the terminal velocity, the acceleration is supposed to be 0. Prevent that round-off error. So these two, I think I'll just copy down one row. And now these four are all new. They've got that if thing. I'll copy that down all the way. So as long as we're not at the terminal velocity, the calculation is as before, but if we're at the terminal velocity, then we make the acceleration 0 and keep the velocity from changing. Alright, so I did get to acceleration 0. Let's see how that compares with the terminal velocity. I got a copy of it. Vm is at the terminal velocity. The graphs are doing what I would expect them to do. The acceleration drops down to 0 and it stays there. Velocity grows to the terminal velocity, 0.14. You can see the number there, and it stays there. Here we got acceleration in the beginning, but then it looks pretty constant near the end there once the thing reaches the terminal velocity. Alright, let's see how this is looking. Let's fix things up so that now we're not going far enough with that value of C. So it's actually pretty close. 0.306, 0.301. No, it's gone a little bit too far. So I got to bulk this up just a little bit. If I go 0.05, now it's not going far enough. So I was at 0.04. It's going to be 0.04 something. I'll call it 0.045. Still not far enough, so I got to get smaller than that to make it so it goes all the way up to the top of the surface in the 2.38 seconds. So 0.042. Try 0.042. Still not high enough. 0.041. Still not going far enough. So this is too big. Try 0.0405. That's too far. I'm going to go Control Z. Control V to go back. Control Y, I'm sorry, to go back to what I just had. So with 0.041, there's too much resistance. It's not going far enough. I'm trying to make these two numbers the same. And so Control Y, when I drop that down to 0.0405, it goes too far. So I need a little bit more resistance than that. Let's try 0.0407. Still going a little bit too far, 0.302 instead of 0.301 something. So too far. I'll bump that up to 8. There. 0.301 to 3 sig figs. This is agreeing. Still going a little bit too far. I think I'll try just tacking on a 5 to that. Not far enough. So it's got to be less than 5. With a 0, it was too far. With a 5, it's not far enough. This value of C is too big, and that means to 3 sig figs, C has got to be 0.0408. So I'm going to write that down. To make it go the right distance in 2.38 seconds, we need C is equal to, okay, I'll say from spreadsheet, C is equal to what is it, 0408? And then we should take a look at, think about what the units are, 0.0408, because with that 5 on there, it was a little bit too big. Without the 5, it was too small. So it's going to round to 0.0408. And then the units are, for C, the idea was that force, I think I want to think about that. The force was equal to the viscous force was C times V. So in order for the right-hand side to come out in newtons, C must have units of newtons per meter per second. And I think that's just the way I'll write it. Newtons per meter per second. This is a lowercase c over here. Gonna make